All right, so what is a polygon? Okay, so let's define what a polygon is. You guys have been using these since probably before you can even remember. Talked about shapes and things. Okay, so a polygon is a closed figure, okay, made up of connected segments. Okay, and those segments, we call those sides. Oh, sorry, yes, I see. And no sides cross. Okay, so it's a closed figure made up of connected segments called sides, and no sides cross. Okay. So, some examples of polygons. And then we'll look at some examples that are not polygons. All right, I'm going to do this on a separate sheet of paper here first. All right, so this shape right here, polygon or not? Polygon, that's right. Okay, so we'll draw that example right there. Okay, so that is a polygon. It's closed. It's made up of connected segments, right? Each one of these parts are segments, and none of the segments cross. So, yep, polygon. Okay, good, good, good. All right, how about... Okay, how about this shape? Is it a polygon?
Yeah.
Okay, so is it closed? Yes. Is it made up of connected segments? Yep, and no sides cross? It's a polygon. Oh boy. Close enough. Okay. All right, good, good, good. All right, let's try another one here. I'll scratch that one out. How about...
Is the circle a polygon?
Great question. Let's take a look.
Is a tire a polygon?
Is a tire a polygon? That's supposed to be a circle. So is a circle a polygon? The answer is it is not. It is not a polygon. Okay, it is closed, but it's not made of segments. Okay, because a circle, right? Can segments be curved? No. And so this, even though you think, oh, but I could just start a segment right here, just wrap around, and then end at the same starting point. Well, no, not the way we define a segment. Segments can't curve, and so a circle is not a polygon. A circle is not a polygon. Okay? Nope. Okay, so the idea is no curves. We don't want curves. Okay? Let's try another one here. Okay, how about this shape? Polygon, yes, good, okay. Alright, so the good thing is you guys kind of already have an innate sense of what they are. Alright, let's try another one here. Polygon, yay or nay? No. Nay, why not? It's not closed, it is open, that's right, okay. So, very good justification too. It is not closed. Okay. All right, let's try another one here. How about this, this little shape right here? It's closed. No, nothing curves. The sides cross. That's right. Lines cross. Yeah. He just probably just because of my drawing, my bad drawing. He's what he thinks. So it yes. So sides, no sides crossing. Okay. So there we go. So there's some polygons and there's some non-polygons. Okay. Now we also need to be able to identify like parts of a polygon. All right. So we'll talk about that here for a second. So the parts of a polygon. So kind of like the anatomy of a polygon. Just like we have parts, and the study of our parts is human anatomy. We'll talk about the anatomy of a polygon. Parts of a polygon. All right. Ooh, cancel. Okay. So polygons have something called vertices. All right. If I draw a polygon over here, I'm going to name these points too. Okay. What is an example in the picture here? So maybe you don't know how to define what a vertice is. Okay. By the way, vertice is plural of vertex. So like a single vertice is called a vertex, but plural is vertice or vertices. Okay. So what's an example of a vertex here? What's a vertex? Josh, can you give me an example in this picture here? What would be like a vertex, you think? Any ideas? I know we haven't defined it yet, but I mean, any thoughts on what it is? Exactly right. A vertex is any one of the points. Exactly right. So a vertice are these are just, or a vertex, these are just the points that define the polygon, the points that make up the polygon, the points that define the polygon. Okay? And so Josh is exactly right. Very good. So like for example, point A there, we can call it a point. We could also call it just a vertex as well. Okay, it's kind of interchangeable. You could use the word vertex, you could use the word point. So you say point A or vertex A, you're talking about the same thing. Okay, so polygons have vertices, they also have sides. Right, and the sides, that's pretty easy. Those are just the line segments. Okay, that connect vertices. Okay, line segments that connect vertices. Okay. So for example, BC, right there, that's a side, right? It's an example of a side. BC, or CD, or DE, or EF, or FA, or AB, whatever you want to say there. Alright, we have one other piece here we need to know about, and that is a diagonal. Okay, a diagonal is a line segment okay, that connects two non-consecutive vertices. Okay, non-consecutive vertices. Okay. So for example, A and B, those are consecutive vertices. They are like one after the other, right? Consecutive just means one after the other. So A, B, those are consecutive. B, C, those are consecutive. C and D, D and E, E and F, F and A, those are all consecutive pairs of vertices. But a diagonal is a line segment that connects two non-consecutive vertices. So for example, A to B connects two consecutive vertices, but A to C, or A to D, or A to E, those would all be examples of a diagonal. Okay, in fact, I'll just draw one in here. So we'll say like from A up to C, that is a diagonal. We know the word diagonal has also the meaning that it's like not a line that goes straight up and down, not a line that goes, straight left and right. It's kind of like slanted. In some cases, our diagonal will do that. In some cases, times they won't. That's the kind of geometric definition. Yeah, Gable?
You're using the word non-consecutive and consecutive.
Yes.
What does consecutive mean?
Consecutive just means like one after the other. So like, the numbers in consecutive order are like 1, 2, 3, 4. The numbers in non-consecutive order is like 1, 9, 4, 10. You know what I mean? You go whatever order you want.
Right. So like, what's it mean like using this figure?
So
like when you say like BC and AF are consecutive lines.
Correct, because they're
AB.
So A and B are consecutive points. They're consecutive because they're like one next to the other. But A, C are not consecutive because to get from A to C, you have to go first through B to get to C. And same thing with like A and E and A and D as well. They're non-consecutive points. Hello, sir. Thank you. Okay. So, one other thing here, to name a polygon, to name it, okay, remember we named triangles, we put a little triangle symbol in front of the shape and we gave it a 3-letter name. In this case, we don't really have like a symbol we put before it, we just write the word polygon. To name this polygon, we just put the word polygon, and then we name it by its points. You don't have to start at A, so we could call this polygon A, B, C, D, E, F. We could call it that, but I mean there's a lot of other options. We could also call it polygon... Oh, sorry, yep. I see what you're saying. I'll zoom it out some there. Okay? So we could call it polygon A, B, C, D, E, F. We could just go around in alphabetical order, that's fine. But you can start really at any point and just go around in order. So for example, I could start at D and then go E, F, A, B, C. There's a lot of options there. As long as you're naming them in an order, right, consecutive points, then that's how you name the polygon. So A, B, C, D, E, F, or D, E, F, A, B, C, or a lot of other options. Okay? All right, questions on any of the parts of a polygon? All good there? All right. So, other things that we need to be able to do. We need to be able to classify polygons. Okay, and these will be really familiar to you as well, because we've used these names before, and so it's just a matter of now, instead of applying them to triangles, we're going to apply them to polygons. Okay, so for example, we can classify polygons as equilateral. Okay, what does it mean to be equilateral? All the sides are equal. Remember, the word lateral means sides, equa means equal, right? So it's equal sides. So all sides, I'm just going to use the congruency symbol here, congruent. So the squiggly with the equals. That's what equilateral means, right? So we've already seen equilateral triangles before. Let's draw that in there, right? We can have equilateral, ooh, that's terrible. Quadrilaterals as well. Okay, lots of options there. All right, then we also have, besides equilateral, we have equiangular. And that, of course, means what? Yeah, that's right. All the angles are congruent. And again, I can draw some pictures of that. We could draw, for example, an equiangular quadrilateral. You guys all know an equiangular quadrilateral by a different name, though.
Rectangle.
It's a rectangle, that's right. A rectangle is an equiangular quadrilateral. Right? You can also have an equiangular triangle as well. Like that. All right. And then, lastly, if a shape is both equilateral and equiangular, what do we call that? You guys remember? It's kind of a weird name to call something that's so special. We call it regular. So if a polygon is regular, it's actually very special. Okay? It's both.
Can it be both?
Equilateral and equiangular. Of course. What's the name of the quadrilateral that is both equiangular and equilateral? A square, that's right. Squares are both equiangular and equilateral. And we know that triangles, if a triangle is equilateral, it also must be equiangular. Okay? And the Pentagon down in DC is roughly a equiangular and equilateral, therefore a regular pentagon as well. Okay? So there's one way to classify polygons. All right.
So you're saying there's only 3 types of polygons?
So we're going to have another way to classify here too.
But a polygon either has to be regular, equilateral, or equiangular.
Well, I see what you're saying. So we don't really have a name for it when it's like besides those 3. It's just now just a plain polygon. So like these are not, I guess, like this does not encompass, yes, all of the polygons, right? Because we have some that are not going to be equilateral or equiangular or regular, and so it was just like just a polygon is all we would call it. It's just a polygon. There's no special additional name we give it, is the idea. Okay? However, we do have some other names there, okay? We've got, for example, concave, or let me kind of put this up there, that way people can get to the bottom piece there. All right? We have concave and convex. And this is where it gets a little bit tricky. Some of you guys maybe remember the word concave from some science classes that you've taken, or convex as well. You talk about like lenses, for example, when light passes through a lens, a concave or convex mirrors too. Okay, so the word concave, we're going to define that one first, and we'll just do it very simple. It's concave if it's not convex. Okay, it's kind of a silly way to do it, but that's what we'll call it. Okay. The shape is concave if it's not convex. Okay? So let me give you some examples of a concave shape. So for example, this shape. It's a polygon that is a concave polygon. Okay. Well, so good question. Anyone want to take a guess here or think? So Skylar, what do you would say here? Why would you call this concave? Yes, the shape kind of bends in on itself. Okay. One way you can kind of help you remember, because it's kind of like, well, how am I supposed to know that concave is the one that bends in on itself and convex is the one that does not bend in on itself? You can think of it like this. It's kind of like, if you look here, if I were to kind of like connect those two vertices, the shape is kind of like, yeah, it kind of looks like an envelope, doesn't it? We can call it like caved in, okay? Like the shape is kind of caved in on itself, right? When you have a cave in, right, that's when the cave kind of collapses on itself. So the shape is kind of like collapsed in. It's bent in on itself, okay?
So every triangle that is not concave, no, just kidding. Every triangle that's not convex is concave.
Correct, but are either of these triangles? Or can you have a concave triangle? Yeah, it's actually impossible to have a concave triangle. What kind of shape is this? How many sides does it have? It's a quadrilateral. Yeah, this is a concave quadrilateral. But yes, the basic idea is that it bends in on itself like that. That's concave, okay? That's the idea.
I thought we just said this were concave.
Yes, these are concave. And we'll look at some convex ones. Convex. Okay? So convex polygons then, and the definition here is pretty tricky, all right? So I might just draw some pictures here, but it's how do I define it over here? I want to see. Okay. No line contains a set of interior polygon. Okay, so it's just not bent in on itself. We'll just do that definition. There is like an official mathematical definition, but I think it's more complicated than what I want to give you guys. So we'll just say that. Okay. And so what's an example of a convex polygon? Well, that's the normal ones you guys are used to seeing, right? So for example, a rectangle, right? A rectangle is a convex polygon, right? Or a pentagon Okay, convex, not bent in on itself. All right, and now we'll finally get to the naming of the polygon by the number of sides. Okay, so now we're going to look at naming polygons. All right, and what's the smallest number of sides that a polygon can have? Yeah, it's 3. The 3 is the smallest number of sides. So, okay. So 3 sides, and we can like draw a little, actually 3 sides, okay, and that's called a what? What's a 3-sided polygon? A triangle. Okay, 4 sides. What do we call a 4-sided polygon? Quadrilateral. Yeah, we got to be careful. Squares, and that's, you know, when for like the longest time, probably guys, again, since you guys were like little babies, right? Your parents were showing you like shapes and things maybe, and you were, you know, they were saying it was always squares, right? We always show like really nice regular shapes, but it doesn't have to be a square. It's just 4 sides. So any 4 sides we call it quadrilateral. All right, 5 sides. Pentagon. That's right, pentagon. Okay. 6 sides. Hexagon. Hexagon.
So what's heptagon?
Heptagon is 7. That is a heptagon. If you say septagon, though, I'll definitely accept that still, but heptagon is what we're going to use. Okay, so 3, 4, 5, 6, 7, triangle, quadrilateral, pentagon, hexagon, heptagon. Okay, 8. Yeah, right, everyone remembers that one because we know that an octopus has 8 legs, right? So, octagon. Also, if you guys like to watch, I think it's octagon. T-A. Let me look at it real quick here. Octa or octo? It's octagon. Now, see, I have octa. It should be an A. That's what I have here. That's what Google says. Octagon. Also, if you guys watch, what is it? MMA, right? Don't they fight in an octagon-shaped ring? That's not a ring; it's an octagon. So, anyway, there you go. Octagon. All right, let's see here. 9 sides. Anyone know what that one is? What's it in Spanish? Yeah, exactly right. Nonagon.
I should learn it like that.
Nonagon. Yeah. Okay.
Well, you have to teach
10 sides, we know that's a decagon, right? Like a decade. And then we kind of stop after that. There are further names. For example, if you really want to know, 11 sides is it's like an undecagon. Okay. 12 sides is a dodecagon. Dodecagon. We kind of stopped after that. It kind of gets a little silly. And instead, pretty much after 10 sides, you don't need to know the name anymore. After 10 sides, okay, for n number of sides, so for example, if you had 20 sides or 30 sides, we just call it an n-gon. So for example, if I want to name a 20-sided shape, I don't come up with some new name, I just call it a 20-gon. Or if I want a 100-sided shape, so for example, 100 sides is called a 100-gon. I know it's kind of silly, but it's just afterward. The names are just, it just kind of gets ridiculous after a while. So
I'm surprised they don't repeat themselves. Not the same name, but the same thing.
Right. So it could be like tridecagon for 13 or something like that. I mean, but
like as numbers do, 1, 2, 3, 4, and then 11, 12, 13, 14. Right.
And maybe they do. Maybe there are further names for these, but we just stop at that point, and we only make ourselves responsible for those. Okay? So, we're going to talk now about the interior angle sum, right? So we already know that triangles, for example, okay, triangles we know add up to, what are the interior angles of a triangle add up to? 180, right? Is that going to be the same? Is that going to be true for, you know, quadrilaterals or pentagons or hexagons? No, not in general. And so what we're going to do is a little activity here that I've got for you guys to kind of help us try and figure this out. All right, so let me pass this out here real quick. Okay. Let's take one and pass it down.
When you're naming a polygon, you're counting the number of sides. Are you counting the points, or are you counting the actual segments?
Well, that's a great question. So, did you notice any difference in those numbers?
No.
They're going to be the same, I think. They should be the same. So you should be able to kind of get with either one. Okay. So we'll kind of do this together, I think, because that might be not a bad idea here. All right. All right, so we just got done talking about the names of polygons and things. And so now let's take a look at this little activity here. All right, try and look at it. Okay. Yeah, you're wanted. Uh-oh, got it there. All right, so this first polygon, its name is what, Jason?
Oh, that one is called a quadrilateral.
I know what you mean, yes. A quadrilateral. Okay, and let's see here. Ryan, what about this one right here, the next one down? Pentagon, you got it.
Yeah, we didn't, me and Ramel didn't get a pick of this.
Oh, I'm so sorry, guys.
Yeah. Where am I, Lord?
Right, yes, that's right. Yes. Segregated.
Yes, this is black.
That's right. All right, next one, polygon name. What's this one's called? What's this one called? Let's go to, sorry, I'm going to pick somebody here. Let's go to, not here. Jaden, what's this one? It's okay. Hexagon, you got it. Alright, and then how about that next one? Oh, he's not here. Krishna, what's this next one called? Heptagon. Heptagon. And then Derek, last one.
I'm guessing
Octagon is correct. Okay, so there are names. Now the next thing it asks for is the number of sides. Well, that should be pretty easy for us to fill out, right? 4, 5, 6, 7, and 8. Now the next one's a bit tricky. It says the number of triangles drawn from one vertex. What that means is we're going to take our shape, and so for example, I'm going to take my square here. I'm going to pick a vertex. I'm going to try and draw a triangle. So the only way I can draw some triangles in here is if I connect from this to this, it creates that diagonal, right? Basically, we're just trying to draw all the diagonals from one vertex. Okay, just from one. I'm sorry?
You can't cross it.
Yeah, so we don't want to draw another diagonal. We only draw from one vertex. So I'm going to pick. I picked this vertex, and I drew from here to there, and so that's it. We just want to. That's our two triangles that we drew there. Okay, from one vertex, just from one vertex. All right. So let's try that again for this next shape, the pentagon here. I'm just going to again pick a vertex. I'll pick this vertex right here. Okay, this one. And let's see. I can't draw the diagonal from here to here because they're consecutive, but I can draw one from here to here. Are there any other diagonals I can draw? There's one more down to there, isn't there? Okay, and that's the only other draw. I can only draw two diagonals there.
If you ask for like an actual diagonal, could you just draw them anywhere, not for just one vertex?
Right. If it asks for any diagonal, yes. But since we're only these specifically say number of triangles drawn from one vertex, number of diagonals really drawn from one vertex. Yeah. So we're just picking one vertex for now. All right. The hexagon. Let's see, again, I'll pick like this point right here. I'll pick that point. All right, so let's see. I can draw a diagonal from here to there, from there to that other vertex, and from there to there. So now how many diagonals do we have drawn there? It kind of looks like a seashell, yeah. We have 3 diagonals there and 4 triangles. So let's see, we have 2 triangles here, we have 3 triangles here, we have 4 triangles there.
Next means the next one will have 5.
The next one, yeah, Jason, very good, is going to have 5. And then octagon's going to have how many diagonals, we think? 6. That's right. So again, if I pick a vertex here, let's see, I'll pick like this vertex maybe. So there to there, there to there, there to there, there to there. And octagon again, I'll go from like there to there, there to there. Ugh, okay. Does anyone see a relationship between the number of sides and the number of triangles that we can draw, the number of diagonals we can draw from one vertex? Yeah, we take away 2, right? It's number of sides, take away 2. Number of sides, take away 2. Number of sides, take away 2, take away 2, take away 2. Yep, they're all 2 less. Okay? Now, what's the degree measure of a triangle? The sum? 180, right? Yeah, so it's 180 for all those, right? Any triangle, the sum is going to be 180, so all these will be 180.
Why is it -2?
I think, well, so that's kind of, you know, a trickier way, that's a good question, trickier way to kind of explain it here. I think partially because, if you think, for example, about the square, right, okay, or this quadrilateral, I should say. I shouldn't say square because we don't have the sides and stuff marked, but if we look at this shape, this quadrilateral, there's only one way to draw, there's 4 vertices, but there's only one diagonal possible. It goes from here to there, and so that then creates those two triangles there. But then when we add another vertex, we add another diagonal, and so that allows us to then create 3. So we're dividing this space that's one thing into 2 things. Now we have two lines here, so that takes the space that was one full thing and divides into 3 pieces, and then 3 divides into 4 pieces, 4 divides into 5, and then 5 divides it into 6. Kind of something like that, I don't know. But it kind of works out that way. There is a relationship there, is the idea. All right. Since there's 2 triangles in here, and each one of those triangles has a degree sum of 180 degrees, what then can we do to find the total interior angle sum for the entire shape? Not divide. If there's 2 of them, and they each add up to 180, and we want to know the total here, we'll multiply. So 2 times 180 is 360 degrees.
Each triangle is...
Each triangle, right, its angles add up to 180, so twice, because there's 2 of them, is 360. Okay? And then for a pentagon, there's 3 triangles, so times 180 is 540 degrees. And then 4 triangles for the hexagon, times 180 is 720 degrees. And then 5 times 180 is 900 degrees.
That's fairly large, actually.
And right, yeah. And then an octagon is 1080 degrees. 1080, that's right. Yeah, that's kind of weird that 1080p does match up with that. I don't think there's any sort of relationship with that. But yeah. So there it is. 360 degrees, 540 degrees, 720 degrees, 900 degrees, and 1080 degrees. Okay? So what's the pattern here? How do we end up? So that means all the angles in a quadrilateral add up to 360 degrees. All the angles in a pentagon add up to 540 degrees. All 6 angles of a hexagon add up to 720. All 7 angles in a heptagon add up to 900. And all 8 angles in an octagon add up to 1080 degrees. That's their interior angle sum. And all 3 angles in a triangle, right, add up to 180. So what's the pattern here? What's the formula that we could say? We start with our number of sides, and then Krishna said we subtracted 2. So we can take the number of sides minus 2. Okay, number of sides minus 2. And then what do we do to those number of sides minus 2? What do we then do to this number here? Multiplied by 180 degrees. That was the number of triangles, right? So n minus 2, that's the number of triangles, times 180.
Why are you doing that?
This is a generic formula for the sum of the angles of any polygon now. N is the number of sides. Okay, minus 2 times 180. And that excuse me, that is the sum of the interior angles of any shape that we come across now. So besides a triangle, by the way, does a triangle work? Well, how many sides does a triangle have? 3. So 3 take away 2 is what? 1 times 180. 180, and that's the interior angle sum of a triangle, right? We can do a square, or a quadrilateral. 4 sides in a quadrilateral, take away 2 is 2. 4 minus 2 is 2. Times 180, that's 360 degrees, and that is the interior angle sum of a quadrilateral. So now we have a generic formula here to find the interior angle sum.
So that's to find everything.
The sum of the angles of a shape.
Okay, so not
Sum
the
of the
specific
angles. Nope, right. Just the sum. Hexagon, heptagon, Heptagon. Okay, heptagon.
How about above hexagon?
How about above hexagon? Pentagon, P-E-N-T-A.
Okay, one more.
And then octagon.
No, the
No?
one on top.
A quadrilateral. Quadrilateral. Okay, so going back to our notes then real quick here, the interior angle sum, okay, formula, so the sum of the interior angles of a polygon equals n minus 2 times 180. Again, n is the number of sides. All right, so for example, we didn't talk about on our little paper there, we didn't talk about, for example, like a decagon. So let's try that. So what is the angle sum of a decagon? So we can answer that question now. Okay? What is the angle sum of a decagon? Or what is angle sum of a decagon? I put the word "the" in there. But what is angle sum of a decagon? So what's the number we're going to put in for n here?
10.
Yeah, 10. Okay, so it'll be 10 for the decagon. Take away 2 times 180. So it's going to be 8 times 180, which is 1,440 degrees. Okay, so that is the interior angle sum of a decagon. All the angles inside a decagon add up to 1,440. Okay, now we can actually do a little bit more than this. We can do a little more than this. What?
Do we want to though?
Well, I think we can handle this. Okay. All right. Thank you, Derek. What is the measure of a single angle in a regular decagon? So now I'm not asking for the sum. We know what the sum is, right? For the sum for any decagon, whether it's regular or not, is 1,440 degrees. I'm not interested in the sum anymore, though. I want to know what is the measure of a single angle in a regular decagon. How can we figure that out? We have enough information here to figure that out. What can we do? Divide our sum by 10. Exactly right. Because what does it mean to be regular? All the angles will be what? The same. And how many angles are in a decagon? 10. And so if we know the sum of the angles is 1,440, and since this is a regular decagon, we can divide that by 10, and we know that each individual angle has to be 144 degrees. Must be. Must be. Okay. So that's how you do it. We divide by the number of angles there for the single angle and a regular. Could we do this same calculation if the shape were not regular?
No.
No. Okay? We need to rely on the fact that it's regular. That means all the angles are the same. If we just are talking about a regular, we're talking about just a plain decagon. All we can say then is the sum. We can't come up with an individual measure because they're all different measures. They'll all be different measures potentially.
So what would you do?
You would need more information, or you wouldn't be asked that question because it's impossible to be done. All right. All right. I think I'm going to stop there. Yes, and we won't worry about exterior angles stuff. Okay.